Assalamualaikum and very good morning. I hope you can hear me. Okay. So we are in week 14 actually. Week 14. So next week will be our last week for this semester. So we have one subtopic need to be covered, which is the three-phase induction uh, machine. Okay. So as mentioned earlier, for this DC motor, the question will be in the final exam. Okay, but the question will be just on the theory part. Okay, and I think for the DC motor, okay, just for your information, for your the DC motor, so we have several types of DC motor. So the one that will be um, in your final exam will be the series DC motor. Okay, and that one will be a theory. Okay, I think maybe on the derivation of the torque speed characteristic based on the armature circuit and field circuit equations. And I think it will be also including this speed control of DC motors, if not mistaken. So, okay, so you can refer to these notes and so on. Okay. And for your information also, uh, so you are SEEEL, right? Program. I don't know whether you will taking another subject which is we call power electronics and drive subject. So this subject or this course for those who take this, it will be taken during your semester during your third year semester two, I think. Okay. So at that in that course, you will actually look at the what I call we'll meet again this DC motor. Okay, and then but we are using what I call the power electronics circuit to control the speed of the DC motor. Okay, so in that course, we will go deeper on how we can use that circuit to control the speed. Okay. So for this course, we just only introduce you how to control the speed of the DC motor. Okay. So as you can see here, we have several methods where we can control the speed. Okay. Because sometimes it's we need the speed to be varied. Okay. So the first method is by vary the voltage supply, which is your voltage terminal, your voltage input to the armature circuit, which is for the rotor, while holding the field constant. Okay, meaning that your flux is fixed. Okay, so there is no change in terms of flux production. Okay, so this one is actually V armature or vitamin is you either you increase or decrease. The second method is by varying the field current. Okay, so IF, we know IF is proportional with flux, meaning that the flux is varied, but the armature voltage is fixed. Okay, so meaning that you changing the flux by changing the field current. The last one, the last method is by inserting a resistance which is in series with the armature circuit. So this one is actually you just include the external resistance which is in series with the armature circuit. Okay, so these are the three methods on how we can control the speed of the motor. Okay, so the first method, as you can see here, is the variation of the supply voltage, which is the first method. But this method can only be applied for separately excited DC motor only. Okay, so this can only be applied for separately excited DC motor. For shunt and series, this type of control cannot be applied. Okay, so how we can control VA? Okay, so actually we can see that in the back EMF equation, where you can see that the voltage of back EMF produced or induced is proportional with the speed of the motor. So based on the equation here, the armature circuit, which is your VA, is equal to IA RA plus EA. Okay, and we consider that this component is usually is very small. Okay, we can see that VA is actually EA. So meaning that we can control the speed by controlling the VA here. Okay, so this one we can substitute with VA, and then from here we manipulate this equation, we rewrite this equation, we can get that your speed can be controlled by VT. Okay, so by controlling the VT, you will actually controlling the speed of the motor. Okay, so when we plot the torque versus speed of the motor, okay, by increasing the voltage armature, you will have a different torque speed characteristic. For example, this is for V1 characteristic, and when you increase the voltage to V2, so you will have this characteristic. And when you increase further the voltage terminal to V3, so you will have this characteristic and so on. Okay, I hope you understand this one. Okay, because as you can see here, for example, for the first characteristic, which is V1, this is the speed. We call this one is the no load speed. This is the speed where the motor will rotate at freewheeling, meaning that there is no load attached, there is no load connected. Okay, for example, the very simple example, if you have, for example, a DC motor, which is a remote controller DC motor, for example. Okay, 12 volt DC motor. Okay, 12 volt DC motor, where you have a battery, positive, negative. Okay, so when it is not connected to the load, it will actually rotate very fast, right? But when you connected this DC motor with a tire, for example, a remote control tire, a car tire, okay, which is a very big tire, so you will see that the rotation is actually become slower. Okay, so that is a different. The no load speed is the speed that when the motor is not loaded. Okay, so when you connected the DC motor with a tire here, where the tire here is we consider to have a constant load, constant torque load. Okay, which is this one is a torque load. Okay, it depends on the weight of the tire. Okay, the intersection between the torque load and the torque speed characteristic of the motor, which is where the voltage supply is V1 here. So the intersection will give the value of the speed of the motor operated. Okay, so that's why, as you can see, when the motor is unloaded, okay, it will rotate at very high speed. But when you connected with a load, for example, this tire here with a constant load, we will see that the speed will reduce. And the value of the speed is depends on the intersection of the torque speed and the torque load. Okay, so as you can see, we have a different reduction. Okay, from here, reduce to a new load, a new speed. Okay, so if you want, for example, for example, this one maybe 1000 RPM. What you need to do if you want to increase the speed to, for example, this one, no load speed is limited to 1500 RPM. Okay, for example, based on this characteristic. When you loaded the motor, so it will reduce this. The reduce will be reduced. For example, 1000 RPM. For example, in your application with the same amount of torque load here, you want to increase the speed to 2000 RPM. Okay, if you maintain the voltage supply at V1, you cannot reach 2000 RPM because the maximum speed for this characteristic when you connect with a voltage supply V1 is 1500 RPM. Okay, how you can increase the speed is actually by increasing the voltage supply to V2, for example. Maybe V2, the no load speed here is maybe 3000, for example. Okay, so you can actually increase the speed of the your motor when you still connected with the load by increasing the voltage supply, meaning that you need to connect another battery so that the total battery value is V2. Okay, so and then based on the intersection between this one, maybe your motor will actually operated at 2000 RPM and so on. Okay, if we want to increase further to 6000 RPM, meaning that you need to increase the voltage supply further so that you can actually uh, have a different characteristic so that you will actually make the rotor to operate at higher speed. So this is actually what happened when you use variation of the voltage supply. Okay, what happened is actually you you change the characteristic of the torque speed of the motor. If you use only single voltage supply, the maximum rotation maybe is around 1500 RPM only. That is actually for the no load speed. Okay, you cannot go further. If you want to go further, 2000 or more, what you need to do is actually to change the characteristic of the motor by changing the voltage supply. Okay, so this one. So variation of the supply voltage is also appropriate to control the series connected. Okay, so this is why for the shunt motor, varying the supply voltage is not an appropriate method because the field current and flux will vary with VT. Okay, because we know that for the shunt which is your RF and your RA here. Okay, so meaning that when you change the voltage, what happen is actually your IF will also change. Okay, so meaning that your IF, when your IF is changed, so meaning that your flux is also changed. So this is not appropriate because for the first method, we need flux to be fixed. Okay, but for shunt motor, when you increase the VT, because VT is parallel with RF, So when you increase the VT, for sure, IF will also change. So we don't want this to be happen because for the first method, the flux must be fixed values. Okay, so that's why for the shunt, it is not appropriate. Okay, so for this method for the series, so it can be applied, but however, the flux does not remain constant in this case. Okay, because for the series, for example, this one, the same thing happened. So we have RF, okay, and then we have RA here, and then we have the back EMF, okay. So this is VT. So when you change the VT, you know that IA is equal to IF, okay. So when you change the VT, for sure, IA will actually change together with IF because IA is equal to IF. So this is not appropriate because flux must be, okay, but in this case, IF is changing. Okay, so that's why for this method, only the separately excited DC motor can be used for this method. Okay, and then the second method is by varying the field current, meaning that this one, VA is fixed, okay, but IF, which is proportional with flux, is varied. Okay, so for this method, we have shunt and separately excited DC motor that can use this method. Okay, in series connected, okay, in series connected, this one, oh, sorry, you have RF, RA, and back EMF. So this one cannot be used because IF is equal to IA. So when you want to change the IF, you will change the IA. And when you change the IA, it will actually have a different effect. Okay. So for series connected, no. Okay. Only shunt and separately excited DC motor can use this method. So this is the torque speed characteristic for the shunt motor. So as you can see here, this is the no-load speed for the first characteristic. If you increase the flux, okay, for example, here, because right now the flux is actually below here. So when you increase the flux, you will see that the no-load speed will actually reduce, okay? And the characteristic also will be different, okay? So for example, if you have your torque load, a constant torque load, which is that your tire, for example, so you will have a different intersection for different speed characteristic. So for example, if you want the speed to be here, so you can use the first IF. So you will actually speeding at this value. If you want to reduce the speed, then you need to increase the IF. So and then you will have the motor to speed at a lower value. Okay. So this is how we can control the DC motor using the second method, which is you control the IF. And the last one is just by inserting the resistance in series with the armature circuit. So for this method, it can be applied to all DC motor, the shunt, separately excited, and also series. Okay, for example, a shunt connected motor with added armature resistance. We denote that the total resistance, okay, no problem. Okay, for example, this one, this is the shunt motor here. So as you can see here, we insert external resistance, which is adjustable, and this is considered as your RA. Okay, so we use a rheostat, okay, which is the adjustable resistor. This is the torque speed characteristic. Okay, so this one, as you can see, if you reduce the value of the RA, so the torque speed characteristic will be changing. Okay, but as you can see, the no load speed is still remain. Okay, this is due to the equation here. When you change the RA, so actually what happened is actually only the torque value and so on will be changed, but the no load speed will be fixed at this its original value. Okay, only the slope will be changed. So when you have a top load, for example, so different intersection will give different value of speed. Okay, so if you want further to increase, then you need to increase the RA, then you can get the different speed. Okay, so I think that's all for the method to control the speed of the DC motor. Okay, only the last method, which is inserting the RA, is applicable for all DC motors. Okay, so this one is a 4 series, I think. Okay, and then see, so this is the last subtopic for the DC machine, which is the DC generators. Okay, so for the DC generators, so as mentioned earlier, the DC motor can be also operated as your DC generator, but this one meaning that your mechanical power will be converting into electrical power. Okay, so but for this, we have the shunt generator, series generator, and separately excited DC generator. But for this syllabus, we only concentrated on the separately excited DC generator only. Okay. So this is the equivalent circuit of the three type of DC generators. So actually the circuit is almost the same, but the difference is actually on the direction of the current. Okay. So right now, as you can see, the source come from the mechanical, the prime mover. So this prime mover is actually anything that actually uh, make the motor possible to rotate. Okay, so this can come from from the turbine, from the hydroelectric turbine, from the heat combustion turbine, and so on. So it will actually rotate this one, and we will produce or induce the what we call the back EMF, which is EA, and the current will flow from the mechanical into electrical. Okay, so the direction of the current is actually going here. Okay, so right now your armature equation, so for motor, your motor equation is VT is equal to IA RA plus EA, right? Or I think you can write VT is equal to EA plus IA RA, right? But for generator, VT is equal to EA, because the direction of the current is going in the reverse direction. So this one is negative IA RA. Or I can write down EA, because EA right now is the source, is equals to your IA RA plus VT. So your VT right now is your V load. Okay. Your VT right now is your V load. So this is the separately excited DC generator. So this is the shunt generator, and this is the compound generator. Okay, so compound is actually this circuit is a combination of series and shunt. But this one will not be covered. Okay, we will only concentrating on the separately excited DC generator. So I think this one you can read this one. Okay. Okay, so the equivalent circuit for separately excited DC generator is shown as previously picture. A prime mover drive the armature shaft at angular speed, which is omega m, and the external DC source, which is a VF, supply IF to the field coil, this one. Okay, so we have external voltage field supply to supply the field circuit. Okay, so because of the drop across the armature resistance, the load voltage will decrease when I load is increased. Okay, so right now, as you can see here, we have the RA. So meaning that when you increase the IA, so there will be a voltage drop across the V load here. Okay, because of the increasing of the IA. So this one can be shown in this diagram. So this is your VL, which is actually in generator is your VA or VT. And this is your IL, which is equivalent to I armature. Okay. So as you can see here, so this is the line of the V voltage across the voltage VL for the separately excited DC generator. When you increase the IA, you will see that the voltage, okay, the voltage load will actually reduce, okay, because of we have IARA, voltage drop across the resistance. Okay, so this is the line for the separately excited DC motor, DC generator. And this is the line for the shunt connected DC generator. So as you can see, the voltage drop for shunt generator is much worse because it has what we call the field weakening effect. Okay, so field weakening effect. So when IA is increased, IF is reduced. Why? Because when you look at the shunt connected here, okay, so this is your IL. So when your IL is increased, definitely IF will reduce, right? Okay, because I source is equal to I load plus I.
Dua aja mau goreng tadi awal setio malas jalan dua aja lah.
Hello? There's a disturbance. You want? Okay. So when you have IL is increased, okay, IL is increased, so IF will definitely reduce. And when IF is reduced, so meaning that your flux will also reduce. So this is when you reduce the flux, meaning that your field will actually weaken. Okay, so that's why we have what we call the field weakening effect here. Okay, that for generator separately excited DC generator is much better compared to the shunt generator. And then the same performance characteristic or the performance criteria is we need to use what we call the voltage regulation. Okay, so V no load minus V full load over V full load, where your V no load is actually the no load values when I load is equal to 0. Okay, and the performance calculation, you can use this equation. Same, we can still apply the DC motor for the DC generator. Okay, but the difference is actually on the armature circuit equations. Right now, your voltage source is EA. Okay, so please mention that your voltage source right now is EA, RA, and this is your IA, and this is your load, which is your VL. So EA is equal to RA IA plus VL. Okay, that is the only difference between generators and the DC motor. Okay, the same equation for the back EMF induced, the torque produced, the same. Okay, so this one, the armature circuit and the field circuit. So, and then another criteria is on the efficiency, which is your P out over P in. Okay, so from the generator itself, the P input is actually from the mechanical. So P in is equal to the torque input multiplied with the speed of the prime mover turbine here. And then we have the friction and windage losses. So this one is actually a mechanical losses. Okay. And we have also eddy current and hysteresis losses. So this one we call electrical core losses. Okay. And then after that, then we can calculate the power developed by the motor due to the rotation of the prime mover, which is T developed, the torque developed by the motor multiplied with the speed omega m. And this is actually equals to the voltage induced, the back EMF of the voltage induced inside the generator multiplied with the current induced. And then we have two losses here, which is the armature losses and also field losses. So that, but this field losses is for shunt and compound. Okay, meaning that for the separately excited DC motor, we have only one losses, which is the armature losses. And lastly, the P out, which is this is electrical output. So simply just multiply the voltage load multiply with the current. So this is example. Okay, so we take a break about 5 minutes so that you can actually try to comprehend this example. Okay, so right now is 7 minutes, so we start 9 9:12. Okay, so take a break about 5 minutes. Okay. 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 We can continue, I think. So we have separate excited DC generator. So I think I can show here. We have the back EMF, okay, and then we have RA, and this one is your current IA, and this is your load, your electrical load, which is your VL, and we have the another circuit, which is the field circuit. Okay, so we have this one VF, okay, IF, and this is your RF with adjustable resistor here with the R adjust. Okay, so it said that we have the VF 140 volt, RF is 10 ohms, and its R adjustable is 4 ohms, and RA is given 0.065. The prime mover rotates the armature at speed of 1,500 RPM. So the speed is 1,000 RPM. So the first one, determine the field current. So this is a very simple one. Determine the field current. You need to concentrate on the field circuit here. So your IF is equals to VF over R. Okay, your R total. So 14 volt, 140 volt over your total resistance, which is 10 plus 4. So this one 14 ohms. So you will have 10 ampere. Okay. So that answering the first questions, the field current. Okay. And the second question is the no load voltage. Okay. So you need to look at the armature right now, the armature circuit. So from the armature circuit, we know that your voltage source right now is EA is equal to IARA plus VA. So when you say that there is no load, meaning that your circuit is disconnected from the load here. Okay. So when there is no load, meaning that your IA is 0. So this one is 0. So meaning that your VEA is actually your V no load. Okay. So your V no load is actually your voltage source, the voltage induced at this one. Okay. So how to calculate your EA? So right now the motor is speeding at 1,000 RPM. Okay. This is the graph shows the EA with the IF. So right now my IF is 10 ampere. Okay, the field that the current that is produced by the field current is 10 ampere. So from here we can see that the graph for when your current is IF, the voltage induced is actually 280 volt. Okay, but you cannot use this directly as your EA. Okay, because this is for when the speed is 1,200 RPM. The motor for this question is running at lower speed, which is 1,000 RPM. So meaning that the value is not 280. So to calculate what is the voltage induced during the speeding of 1,000 RPM, so you can always use the formula here. The ratio between voltage induced at 1,000 RPM and the voltage induced at 1,200 RPM is equals to the rotation of the motor. Okay. So from there, you can get the voltage induced when the rotation is 1,000. So this one will be 1 over 1.2. So this one 1,000 over 1,200 multiply with the voltage induced, which is 280 volt. So you will get this one as around 233.3 volt, if not mistaken. Yes. Okay, 233.3 volt. Okay. So we know load using this equation, because when there is no load, IA is 0, So definitely your voltage no load is equals to your source, which is EA 233.3 volt. So this answering the second questions. Okay. The third question is calculate the values of the voltage no load. Okay. So from the questions, he said that when the generator is connected to a full load, uh, the okay, a current of amount of 200 RPM will actually flowing when you connected with a full load. Okay, so based on the equation, IEA is equal to IARA plus V load. Okay, so right now your V load is equals to IARA. Sorry, this one should be EA minus IARA. So your EA right now that you have obtained is 233.3 minus the current value is 200 during full load, and the RA is given 0.065. Okay, so this one will give you 233.3 minus 13 volt. So this one I think 220.3, I think 233.3 minus 13, 220.3 volt. So this is your V during full load. Okay, so this answering the full load question. And then what is the percentage of the voltage regulation? So the percentage of voltage regulation, VR, is equals to V no load minus V full load over V full load. So this one 200 and this one I think V no load minus V full load is 13 volt over 220.3. So this one should be 0.05 or I think 5.9%. So 5.9% is considered good. Okay. So I hope you can follow me. You still follow me? This is this is recorded. Okay. I think if you don't understand, then I think you can always refer to this video. I will upload this video soon after I have got the video from. This video actually will be stored in the cloud. Okay, with the Webex cloud. Then after they have compiled, so they will give the link to me to download. So it takes I think, several hours, I think, for them to compile. Okay, so we have finished on the voltage regulation. Okay. I hope any questions? So if there is no question, then I think we can proceed with the next questions. So assuming that the overall efficiency of the machine, not including the powers, not including what you call the power supply to the fuel circuit and so on. Okay. the machine is 85%. So determine the input torque, the developed torque, the losses associated with the friction, windage, all. Okay, assuming the efficiency is around 85, not including the power supply to the field circuit. So meaning that the field circuit here is not considered. Okay, we only consider the losses at this armature circuit only. So it gives you the efficiency is 85. So P out over P in is around 0.85%, 0.85. Okay. P out is electrical output, which is you multiply with IA multiply with VL. Okay. Right now your IA is 200 ampere during the full load, and your VL we have calculated earlier is 220.3 volt. So your P out is 200 multiplied 20, 220.3. So you will have 44.06 kilowatt. So this is your P out. Okay, so meaning the P in is equals to 44.06 kilowatt over 0.85. So this is your P in, which is 51.83 kilowatt. And we know that P in is actually a mechanical input, mechanical input. So this one is actually equivalent to T torque input multiplied with the speed of the motor. Okay, so the speed of the motor right now is 1000 RPM, but you need to convert 1000 RPM into radian per second. Okay, so your torque input is 51.83 kilowatt over the speed you need to convert. So 1000 multiplied with 2 pi over 60. So this one will give you two. I think 495 Newton meter, if not mistaken. 495 Newton meter. Okay, 494 I think. 494.6. Okay, so that is your torque input. So we have answering this one. The next is actually to determine the developed torque. Okay, so developed torque is actually you can get from the P developed. Okay, you see from here, the equation here. So P developed by the generator in electrical form is actually EA multiplied with IA. Okay, so right now your EA we have already obtained, which is 233.3 multiplied with IA, which is 200. This one will give you 233.3 multiplied with 200 is 46.66 kilowatt. Okay, and this one is equivalent to torque developed in mechanical form multiplied with the speed. So from that you can get your T, the torque developed by the generator, 46.66 kilowatt over the speed of the motor is 1000 RPM multiplied with 2 pi over 60 because you want to convert into radian per second. So this one will give you the answer of 446 Newton meter. Okay, so we have answering this this question. And then the last one is the losses associated with the friction, windage, eddy current, and hysteresis. So from the power flow here, we can see that the difference between P in and P developed by the generator is actually the amount of losses of friction, windage, and eddy current and hysteresis losses. So meaning that to get this amount of losses, what you need to do is just P input over your P develop, which is the P input, if not mistaken, is around 51.76 that we have calculated earlier, minus the power developed by the generator, 46.66 kilowatt. So this one is actually, the losses is around 5.16 kilowatt. So we complete this example. Okay, so I think that's all. This example conclude the subtopic of the DC machine. Okay, I think that's all for today. And we meet again on Thursday with a new subtopic, which is the last subtopic, which is the three-phase induction motor or machine. Okay, I think that's all. Thank you very much for your attention throughout this online class. Okay, inshallah I will post this recorded video in our group. Okay, so thank you very much. Okay, thank you.